Hello, I am Alex, host of the AI Research Roundup. Today is May 9th, 2025. We are looking at a paper from Hugging Face's trending list, published 10 days ago, Grokking in the Wild, Data Augmentation for Real-World Multi-Hop Reasoning with Transformers. This paper explores how transformers, AI models for language, can improve multi-step factual reasoning, so connecting several facts. They address sparse knowledge graphs, organized fact databases, by adding synthetic data. This aims to increase a key ratio. Phi_r, the proportion of complex, inferred facts to simple, atomic ones, to trigger grokking, a shift from memorization to genuinely understanding underlying patterns. Alright, so to visualize how they boost this key phi_r ratio, this figure presents a small example knowledge graph. Initially, we see a few items, or nodes, like Obama and Michelle, connected by original relationships in blue, such as, quote, wife of. These allow for a couple of inferred, multi-step facts. Then, new synthetic relationships and nodes are added, shown in red, like Michelle being, quote, sister of Bob. This expansion significantly increases the number of possible inferred facts, relative to the simple, directly stated ones, pushing that phi_r ratio up, in this illustration, from about 0.66 to 1.2. Building on that idea of increasing the phi_r ratio, the authors provide this key notation table to clarify the symbols used. So we see V for entities or nodes, and R for the types of relationships in the knowledge graph. Then, F_A represents atomic facts, which are simple, single-step pieces of information. F_I stands for inferred facts. These are the more complex, multi-step connections. And, of course, there is phi_r, that crucial ratio of inferred to atomic facts. The table also introduces phi_g, the minimum value of that ratio needed for the model to achieve successful grokking. Okay. Now this table presents the Structured 2 Wiki Multi-Hop QA results. That is a dataset designed to test multi-step factual reasoning. It compares different methods, including a standard GPT-2-small and their Grokking GPT-2-small. We see accuracy scores for both in-distribution, or IID, data, which is data similar to what the model trained on, and out-of-distribution, or OOD data, which is new, unseen data. Notably, their grokked model shows very high out-of-distribution accuracy on comparison tasks, hitting 0.96, much better than the other models listed. So, following those impressive out-of-distribution scores from the table, these plots in Figure 4 really visualize that grokking effect. Panel A compares out-of-distribution accuracy, so how well the models perform on completely new data for the original versus their grokked GPT-2-small. Notice the dashed line, representing the grokked model, showing a significant jump in accuracy later in training. Then, Panel B details the training curves for the structured comparison task, where the blue line, the out-of-distribution accuracy, again shows that characteristic late-phase jump after many training steps, a hallmark of true grokking. This clearly demonstrates the impact of their data augmentation. Alright, so these visualizations really drive home the point. In essence, this work shows that by cleverly adding synthetic data to real-world knowledge graphs, those large databases of facts, we can significantly boost that crucial phi_r ratio. This increase triggers grokking, that amazing shift from memorization to understanding in transformer models. This leads to much better out-of-distribution accuracy, meaning strong performance on new information, even if some added data was not strictly factual. It is a powerful idea for building more capable AI. Thanks for tuning in to the AI Research Roundup.